When the sky weeps, where does the water slip? Between the walls so high, the ponds of rain lie. Today, we explore this poetic mystery in the world of algorithms, trapping rainwater, the second problem. In this problem, we are given a two-dimensional matrix called height map. Each cell represents the elevation of land at that point. When rain falls, water gets trapped between the elevations, forming ponds. Our goal is to compute the total amount of water that can be trapped after the rainfall. In the first example, we have a 3 by 6 matrix. After the rainfall, we observe two ponds. One stores 1 unit of water, while the other stores 3 units. Together, the total trapped water is 4 units. In the second example, we are given a 5 by 5 matrix. The central cells are lower than the boundary. As a result, the basin holds 10 units of water in the middle. This demonstrates how boundaries play a crucial role in trapping water. Let us note some key points. First, water cannot escape outside, so the boundaries determine the limits. Second, water is always trapped relative to the lowest boundary height. Finally, this problem is an extension of the classic one-dimensional trapping rainwater problem into two dimensions. Our approach will be based on a main heap, also known as a priority queue, combined with breadth-first search. We begin from the boundaries and expand inward. This ensures that the lowest walls are always processed first. Whenever a neighboring cell is lower than the current boundary, water is trapped there and the boundary height is updated. Here is the step-by-step algorithm. First, push all boundary cells into the main heap. Second, mark them as visited. Third, while the heap is not empty, pop the lowest cell. Then check all 4 of its neighbors. If a neighbor is unvisited, we check if water can be trapped. If yes, we add it to our total and then push the updated neighbor back into the heap. Let us dry run the first example. We start from the boundary where the minimum height is 1. Moving inward, cell at position 1 1 traps 1 unit of water. Cell at 1 2 traps 2 units and another cell traps 1 more unit. The total adds up to 4 units, which matches our expected result. The pseudocode clearly shows the flow. We initialize the heap with boundary cells, mark them visited, and set total water to 0. Then while the heap is not empty, we pop the lowest cell, check its neighbors, and trap water whenever possible. This ensures correctness while keeping the logic clear. In the first part of the C++ solution, we define the function trap rainwater. We first handle the base case where the matrix is too small to hold any water. Then we initialize a visited matrix to keep track of cells we have already processed. We also create a main heap or priority queue, which will help us always process the lowest height cell first. In the second part, we insert all boundary cells into the main heap. These represent the outer walls of the elevation map, where water cannot escape. At the same time, we mark these boundary cells as visited. This step is critical because it sets up the initial walls from which we will expand inward. In the final part, we process the heap until it becomes empty. For each cell, we check all 4 neighboring directions. If a neighbor is unvisited, we mark it visited. If the neighbor's height is lower than the current boundary, we calculate the water trapped as the difference. Then we push the neighbor into the heap with an updated height equal to the maximum of its own height and the boundary. When all cells are processed, we return the total amount of trapped water. Analyzing complexity, the time complexity is big O of m times n log of m times n because each cell is pushed into the heap once. The space complexity is big O of m times n required for the visited matrix and the heap. This is the efficient for the problem constraints. In conclusion, the two-dimensional trapping rainwater problem can be solved by expanding from the boundary using a main heap. This ensures that the lowest walls are always processed first. The combination of breadth-first search and priority queue gives us an elegant and efficient solution. Just like in nature, water always finds the lowest path, and our algorithm mimics this beautifully. Thank you for your attention.